There is a rock almost the size of the Empire State Building falling toward Earth right now, and in April 2029, you will be able to see it with your naked eyes as it slips through our satellite belt. While the world obsesses over interstellar comets wandering harmlessly near Jupiter, this thing named after the Egyptian god of chaos is closing in kilometer by kilometer, day by day. NASA says we are safe, that the math has been checked and rechecked, but new thermal forces are pushing it off course, tiny nudges that compound over time, and the scientists who track these objects are watching very, very carefully. Stay with me until the end, and I will show you why Apophis is not just another space rock, but a countdown we cannot ignore. If these questions about Apophis and our cosmic neighborhood have pulled you in the way they have pulled me in, make sure to like this video and subscribe for updates as we move closer to the most significant asteroid flyby in recorded history. Leave a comment with where you're watching from, what hour it is there right now, and your take on whether the official narrative about planetary defense is as solid as they claim it is. Part 1. The God of Chaos approaches. Picture this. Somewhere beyond Mars, a mountain of rock and metal the size of the Empire State Building is falling toward Earth at speeds that would obliterate every speed record ever set by human hands. You cannot see it yet. Most people do not even know its name. But on April 13th, this thing will arrive. It will not merely pass by our planet. It will slice through the orbital ring where our satellites live, coming so close that people in parts of Europe, Africa, and Asia will be able to see it with their naked eyes as it carves across the night sky like a celestial blade. NASA has named it Apophis after the ancient Egyptian god of chaos and destruction, and while scientists assure us that we are safe, that the calculations have been run and rerun, that the margins are known and the threat is contained, there is something they are not saying quite as loudly. The rock is drifting. New forces barely understood until recently are pushing Apophis off its predicted course. The error bars are shrinking. Yes, but they have not disappeared. And in the silent mathematics of orbital mechanics, even the smallest deviation can mean the difference between a cosmic spectacle and an extinction-level catastrophe. Meanwhile, out near Jupiter, another visitor has captured the public imagination. Comet 3C, Atlas, an interstellar wanderer that originated somewhere beyond our solar system, has been making headlines as it traces a path through the outer reaches of our neighborhood. It is scientifically fascinating. Absolutely. Researchers are studying its composition, trying to understand what materials exist in other star systems, what the building blocks of distant worlds might look like. But here is what matters for our immediate survival. 3I. Atlas poses zero threat to Earth. Its orbit keeps it millions upon millions of kilometers away from our blue marble. It is a cosmic curiosity, a visitor from the interstellar void that will pass through and leave without incident. We love to romanticize comets. They have tails that glow. They move with ethereal grace. They feel like messengers from the universe. Asteroids, by contrast, are rocks. Boring, brutish chunks of debris left over from the solar system's formation. But this bias, this preference for the pretty over the practical, blinds us to which objects actually matter. Apophis matters. It has been on our radar since 2004, when astronomers first calculated its orbit and realized with growing alarm that this thing was going to come uncomfortably close to Earth. Initial estimates gave it a 7% chance of impact in 2029. That might not sound like much, but in the world of planetary defense, it was enough to elevate Apophis to a level 4 on the Torino scale, a classification reserved for objects that warrant serious attention from astronomers worldwide. For a brief, terrifying moment, humanity had to confront the possibility that a chunk of space rock, 340 meters across, might actually hit us. Subsequent observations thankfully eliminated the 2029 impact scenario. Then they eliminated 2036. Then they eliminated every other close approach for at least a century. NASA's official position is unambiguous. Apophis will not hit Earth. The risk has been calculated, recalculated, and effectively removed from the danger list. But here is where the story gets complicated. Because while the immediate threat has been ruled out, the long-term picture is messier than the press releases suggest. Scientists have recently incorporated something called the Yarkovsky effect into their models. This is a subtle force, almost ridiculously small on the scale of celestial mechanics. But it is real and it is measurable. When sunlight hits an asteroid, it heats one side. As that side rotates into shadow and cools down, it releases infrared radiation back into space. That radiation, faint as it is, produces a tiny push over decades and centuries. These tiny pushes add up. They can shift an asteroid's orbit by kilometers, sometimes more. For Apophis, scientists have now measured this effect and incorporated it into their predictions. The good news is that the uncertainty for the 2029 flyby is now razor thin, just a few kilometers. The unsettling news is that this tiny thermal force opens up questions about what else we might be missing. If sunlight itself can nudge a rock off course, what about micrometeoroids? What about gravitational interactions with other asteroids? What about forces we have not even identified yet? The media tends to present science in binary terms. Either we are safe or we are doomed. Either the threat is real or it is fake news. But the universe does not operate in binaries. It operates in probabilities, in margins of error, in unknowns that shrink only as our observations improve. Right now, the official story is that Apophis poses no danger for at least 100 years, and that is probably true. But probability is not certainty. Models are only as good as the data they are built on, and the data we have on Apophis, while extensive, is still incomplete. We do not know its internal structure. We do not know if it is a solid chunk of rock or a loosely bound pile of rubble held together by its own weak gravity. We do not know exactly how its surface reflects and absorbs heat, which directly affects the strength of the Yarkovsky push. These are not trivial details. They are the variables that determine whether our predictions hold or crumble. So, while the world watches 3i, Atlas glide harmlessly through the outer solar system, a far more immediate concern is ticking down like a cosmic countdown. April 13th. Liaocenling Arshizhou. Mark it on your calendar. Because on that day, whether we are ready or not, whether our models are perfect or flawed, Apophis will arrive and the whole world will be watching. Part 2. The mathematics of near misses. Let us talk about how we actually track these things, because the process is equal parts brilliant and terrifying. When astronomers discover a new asteroid, they start with a handful of data points. Positions in the sky observed over several nights. From those positions, they calculate an orbit, but early orbits are rough sketches, not finished portraits. The uncertainty is enormous. The asteroid could be on a path that brings it dangerously close to Earth, or it could be on a path that keeps it safely distant. You simply cannot tell from a few nights of observation. So astronomers keep watching, night after night, month after month, sometimes year after year. They collect more data. Each new observation narrows the uncertainty. The orbit becomes clearer. The predictions become sharper. For most asteroids, this process is straightforward. You watch. You calculate. You confirm that the object poses no threat. And you move on to the next one. But Apophis was different from the start. When it was first discovered in June of 2004, astronomers immediately recognized it as something worth monitoring closely. Its orbit brought it near Earth, and the initial calculations suggested that a future close approach was not just possible, but likely. Then on December 27th of that same year, updated observations refined the orbit, and suddenly the picture got much worse. The new calculations indicated that Apophis might actually hit Earth during its close approach on April 13th. Liaocenling Arshizhou. The probability was small but non-negligible. Around 2 by 500T. That was enough to push Apophis to a level 4 on the Torino scale, a rating system designed to communicate impact hazards to the public. Level 4 means an object that merits attention by astronomers worldwide. An event that is uncommon, but not unprecedented. It was the first time any asteroid had reached level 4 since the scale was created. The astronomical community went into high alert. Over the following months, more observations poured in. Astronomers around the world turned their telescopes toward Apophis, gathering as much data as they could, and slowly the uncertainty shrank. By August 2025, new radar observations from the Arecibo and Goldstone facilities provided incredibly precise measurements of Apophis's position and velocity. These observations effectively ruled out the 2029 impact scenario. The asteroid would pass close. Yes, but it would not hit us. The Torino scale rating dropped to 0. The immediate panic subsided. But the story was far from over, because now scientists had to consider a new wrinkle. Gravitational keyholes. These are tiny regions of space, sometimes just a few hundred meters wide, through which an asteroid can pass and have its orbit altered by Earth's gravity in such a way that it returns on a collision course during a future approach. For Apophis, the concern was the 2036 encounter. If Apophis passed through a specific keyhole during the 2029 flyby, it could be nudged onto a path that brought it back for a direct hit 7 years later. This is where things get conceptually wild. Imagine playing cosmic billiards where the pockets are invisible, scattered across space, and hitting one pocket sets up a shot that might not land for decades. Gravitational keyholes are real. They have been mathematically proven, and for a brief period, Apophis seemed like it might thread one of these needles. Fortunately, additional observations ruled out that scenario as well. The 2036 impact was eliminated, then the 2068 impact, one by one. The threatening scenarios fell away as the data improved. By 2021, NASA officially removed Apophis from its risk list for at least 100 years. The message was clear: we are safe. Apophis is not going to hit us. Except that is when the Yarkovsky effect entered the conversation. Scientists had suspected for years that thermal forces could influence asteroid orbits, but measuring the effect on a specific object required incredibly precise data. In 2021, astronomers used radar observations to detect the Yarkovsky acceleration on Apophis for the first time. They measured how much the asteroid was drifting from its predicted path due to the uneven heating and cooling of its surface. The drift was tiny, less than 200 meters per year. But it was measurable, and it was real. This discovery fundamentally changed how scientists model Apophis's long-term orbit. Before, they could assume the orbit was determined purely by gravitational forces, the Sun, the planets, and other massive bodies. Now, they had to account for a non-gravitational force that depends on the asteroid's size, shape, rotation rate, and surface properties, all of which are still not perfectly known. The Yarkovsky effect is not going to make Apophis hit us in 2029. The calculations are solid on that point. The uncertainty in the flyby distance is now around plus or minus 3 kilometers, which sounds like a lot until you remember that Earth itself is over 12 null kilometers in diameter. We are not talking about a near miss. We are talking about a close pass with a known and manageable margin of error. But here is the thing that keeps planetary defense scientists up at night. The Yarkovsky effect accumulates. It is a small push. Yes, but it is a constant push. Over decades and centuries, those small pushes can move an asteroid by thousands of kilometers. And if our models of the effect are even slightly wrong, if we have misjudged the asteroid's thermal properties or rotation rate by just a bit, then our predictions for encounters in 2050, 2050, or 2100 could be way off. This is not science fiction. This is the cutting edge of orbital mechanics, and it is why, even though NASA says we are safe, the scientists are still watching, still measuring, still refining, because in space, the difference between safe and catastrophic can be measured in meters, and we are still learning how to measure. Part 3. The closest encounter in human history, April 13th. 2050. Let that date sink in for a moment. It is not some distant future abstraction. It is less than 5 years away. People who are in high school right now will be starting careers. Children who are just learning to read will be teenagers. And on that day, something will happen that no human civilization has ever witnessed with modern technology. A mountain-sized asteroid will pass so close to Earth that it will fly underneath our geostationary satellites. We are not talking about a distant speck visible only through telescopes. We're talking about an object that will be bright enough to see with the naked eye, cruising across the sky like a slow-moving star, visible from Europe, Africa, and Western Asia. People will be able to walk outside, look up, and watch as 340 meters of primordial rock slides past our planet at a distance of roughly 31.000 kilometers. That is closer than the orbit of most communication satellites. It is closer than the GPS network. It is so close that Earth's gravity will physically affect the asteroid, potentially changing its rotation rate and reshaping its surface. To put this in perspective, consider what 31.000 kilometers actually means. The International Space Station orbits at about 400 kilometers up. The geostationary satellite belt, where most of our communication and weather satellites live, sits at roughly 35.786 kilometers. Apophis will pass between Earth and that satellite belt. It will thread the gap. Now, before you panic, scientists have calculated the trajectories and confirmed that Apophis will not hit any satellites. Space is big, even in the crowded regions near Earth, and the chances of a direct collision are vanishingly small. But the symbolic and practical implications are staggering. We have built a technological infrastructure in orbit that our modern civilization depends on: television, internet, GPS, weather forecasting, military communications. All of it relies on satellites that orbit in that ring. And for the first time in history, a natural object large enough to cause regional devastation if it hit Earth will pass through that zone. Astronomers predict that Apophis will reach a peak brightness of around magnitude 3.1 during the closest approach. For those unfamiliar with astronomical magnitude scales, that is roughly as bright as the stars in the Big Dipper. Not blindingly brilliant, but easily visible to anyone with clear skies and a decent view of the horizon. The asteroid will move relatively slowly across the sky, not streaking like a meteor, but crawling like a satellite. It will be surreal. Imagine standing outside on a spring evening, looking up and seeing a moving point of light that you know is a rock the size of a skyscraper, passing close enough that if Earth's gravity were just a bit stronger, or if the timing were just a bit different, it could be pulled into a collision course. That is the reality of April 13th. Liaotenling Oshizhou. It is not a drill. It is not a simulation. It is happening. The scientific community is treating this encounter as an unprecedented opportunity. NASA has already announced plans to send the OSIRIS-APEX spacecraft to rendezvous with Apophis shortly after the 2029 flyby. OSIRIS-APEX is the renamed OSIRIS-REx mission, which successfully collected samples from the asteroid Bennu and returned them to Earth. After completing that mission, NASA redirected the spacecraft toward Apophis. The plan is for OSIRIS-APEX to arrive at Apophis in 2029, study how the close encounter with Earth has affected the asteroid, and gather data on its composition, structure, and rotation. Meanwhile, the European Space Agency is developing its own mission called Ramses, which is designed to observe Apophis before, during, and after the flyby. These missions will give scientists an unprecedented look at how a planetary close encounter affects an asteroid in real time. It is like getting a front-row seat to a natural experiment that happens once in a millennium. But beyond the science, there is a deeper psychological impact to consider. For most of human history, the sky has been a distant, untouchable realm. The stars, the planets, the moon, they were objects of wonder and mythology, things that affected us only indirectly through gravity and light. But in 2029, that separation collapses. The cosmos will reach down and touch our orbital infrastructure, an object from the primordial solar system, a relic from the age of planetary formation, will pass close enough that its trajectory will be visibly altered by our planet's gravity. Earth will pull on Apophis, and Apophis will pull on Earth. The forces are mutual, even if the effects are asymmetric. This is not a distant abstraction. This is a physical interaction between our world and the void. And it raises an uncomfortable question. If this rock can come so close without hitting us, what about the next one? What about the ones we have not found yet? What about the ones that will not give us decades of warning? Because here is the uncomfortable truth. Apophis is only as well studied as it is because we got lucky. We found it early. We had time to observe it, to refine the orbit, to rule out the impact scenarios. But there are thousands of near-Earth asteroids out there, and we have not catalogued all of them. Some are in orbits that make them difficult to detect. Some are dark, reflecting very little sunlight. Some approach from directions where our telescopes are not looking. And while the odds of any single asteroid hitting Earth in our lifetimes are low, the odds of an impact happening eventually are 100%. It is not a question of if. It is a question of when and whether we will be ready. Part 4. What the flyby will teach us and what it will not. Scientists like to talk about Apophis as a learning opportunity, and they are absolutely right to frame it that way. But let us be clear about what we are actually going to learn and what remains frustratingly unknown. The 2029 encounter will provide data that we simply cannot get any other way. When Apophis passes through Earth's gravitational field, our planet will exert tidal forces on the asteroid. These are the same forces that cause ocean tides. The stretching and squeezing that occurs when a massive object like the Moon pulls on different parts of Earth with slightly different strengths. For Apophis, which is much smaller and less massive than Earth, the effect will be more pronounced. Earth's gravity could change the asteroid's rotation rate. It could cause surface materials to shift or slide. It could even trigger small landslides if the asteroid is a loosely bound rubble pile rather than a solid chunk of rock. Scientists will be watching all of this with radar and optical telescopes, measuring every wobble, every shift, every tiny change. This data will help answer fundamental questions about asteroid composition and structure. Is Apophis monolithic or fractured? Is it dense and metallic or porous and rocky? How much of its mass is locked in a solid core versus scattered in a loose shell? These are not academic curiosities. They are practical questions that directly impact planetary defense. If we ever need to deflect an asteroid, the method we choose depends entirely on what that asteroid is made of. A solid rock can be nudged with a kinetic impactor, a spacecraft that slams into the surface and transfers momentum. But if Apophis is less a single boulder and more a loose rubble pile, it might absorb an impact like dry sand, letting fragments drift apart for a breath before their weak gravity gathers them back again. Understanding that internal architecture is not optional, it is the hinge on which real defense strategies swing. Apophis, because it passes so close, can reveal its nature in ways distant points of light never truly can. And yet, here is what the flyby will not tell us. It will not tell us whether Apophis poses a long-term threat. The 2029 encounter is only one data point. Even if it is a brilliantly measured one, it will refine our models. Yes, it will reduce uncertainties. Absolutely, but it cannot erase the possibility of a future impact decades or centuries from now, because orbital mechanics is, at its core, a chaotic system. Small changes now can grow into large effects later. This is the essence of chaos theory, the mathematical language for systems where tiny differences in starting conditions lead to wildly divergent outcomes. Apophis lives inside that kind of clockwork. Its orbit is influenced by the Sun, by Earth, by Venus, by Jupiter, by Mars, and by countless smaller masses scattered through the solar system. Each influence is small, but together they add up over time, shaping the future one faint tug at a time. And while we can model these influences with impressive accuracy, our models are not perfect. They cannot be. We do not know the exact mass of every asteroid, the exact position of every planet at every instant, the exact strength of every gravitational pull at every moment. We approximate, we estimate, we refine, and we revise, but we do not know with absolute certainty. This brings us to gravitational keyholes, which we touched on earlier, but which deserve a deeper, calme examination. A keyhole is a region of space, often only a few hundred meters across, through which an asteroid can pass during one encounter and have its orbit altered just enough that it returns on a collision course during a later encounter. Think of it as a cosmic game of pinball, where striking a specific bumper sets up a shot toward Earth years down the line. For Apophis, scientists have calculated the locations of several keyholes associated with the 2029 flyby. If the asteroid passed through one of them, it could return on a dangerous trajectory in 2036, or some other future date. The good news is that current models show Apophis will not pass through any known keyholes. The uneasy news is that keyholes are defined by our understanding of orbital mechanics. If that understanding is incomplete, then our map of where the keyholes are is incomplete too. And then there is the Yarkovsky effect, which we keep coming back to because it refuses to behave like a simple, predictable force. The strength of the Yarkovsky push depends on factors we cannot fully measure from Earth. It depends on the asteroid's thermal inertia, the measure of how quickly its surface heats up and cools down. It depends on surface roughness, on color, on composition, on rotation rate, on the precise way sunlight is absorbed and then returned to space as heat. All of these variables feed into a complex equation that determines how much the asteroid drifts over time. Scientists have made their best estimates based on the data available, and those estimates are good, careful, disciplined, earned, but they are not perfect. Over decades, small errors in the Yarkovsky calculation can compound into significant orbital uncertainties. This is why scientists plan to observe Apophis intensively in the years leading up to 2029. The more data they collect, the better they can constrain the Yarkovsky effect. The better they constrain it, the more accurately they can predict future encounters. It is iterative refinement, and it never truly ends. And there is another factor that barely gets mentioned in public discussions. It may be the most unsettling of all: the possibility of a collision with another object. Space is not empty. It is filled with debris, from tiny dust grains to larger rocks and, occasionally, other asteroids. Most of this debris is too small to track, and the odds of any single collision are incredibly low. But over the timescales, we are talking about decades and centuries. The cumulative probability becomes non-negligible. If Apophis were struck by even a small meteoroid at the right angle and velocity, it could change the asteroid's trajectory in ways our models did not anticipate. This is not fear-mongering. It is acknowledged in the scientific literature. Researchers have studied the statistical likelihood of such events and concluded that while rare, they are not impossible. And in a chaotic system, impossible often just means we have not seen it happen yet. So yes, the 2029 flyby will teach us an enormous amount about Apophis. It will refine our models, reduce uncertainties, and give us confidence in our predictions for at least the next several decades. But it still cannot eliminate all doubt, because the universe is not obligated to fit neatly into our equations, and the margin between certainty and catastrophe is thinner than most people realize. Part 5. Cosmic Threats in Context. Now let us zoom out for a moment and place this entire situation inside a broader frame. Apophis dominates the conversation about near-Earth threats, but it is hardly the only object we need to think about. In fact, it is not even the most statistically dangerous asteroid currently on our radar. There are thousands of near-Earth objects, asteroids and comets whose orbits bring them into the vicinity of Earth's path around the Sun. NASA's Center for Near-Earth Object Studies tracks these bodies, calculating their orbits, assessing their potential threat, and publishing regular updates on which ones merit closer attention. At any given time, there are dozens of objects with non-zero impact probabilities in the coming decades. Most of these probabilities are vanishingly small, fractions of a percent or less, but they are not zero. And in the calculus of planetary defense, non-zero is the line that keeps the story alive. Take Bennu, for example, the asteroid visited by NASA's OSIRIS-REx spacecraft. Bennu is slightly larger than Apophis, about 500 meters in diameter, and it has a small but measurable chance of impacting Earth in the late 2100 seconds. The cumulative probability across all potential impact dates is roughly 1 inch 2 Tsebai. That is higher than Apophis's current impact probability for any future encounter. Should we be more worried about Bennu, statistically? Yes, but Bennu's potential impacts are more than a century away, whereas Apophis will make its close pass in less than 5 years. The immediacy of Apophis captures our attention in ways that distant probabilities do not. We fear what is near more than what is likely. It is why people are more afraid of airplane crashes than car accidents, even though cars are far more dangerous. It is why Apophis gets headlines while Bennu gets scientific papers. And then there is 3I, Atlas, the interstellar comet that sparked this entire conversation and set imaginations alight. Let us be absolutely clear. 3I, Atlas poses no threat to Earth. Its orbit keeps it in the outer solar system, millions of kilometers from our planet. It will not come close. It will not impact. It is scientifically fascinating because it originated outside our solar system, giving us a rare opportunity to study material from another star's planetary system. But in terms of danger, it is irrelevant. The reason it captures public attention is the same reason comets have always captured public attention. They are beautiful. They have tails. They move across the sky with a sense of purpose and drama, like quiet messengers. Asteroids, by contrast, are just rocks. They do not glow. They do not stream gas and dust. They are harder to see, harder to romanticize, and harder to get excited about. But from a planetary defense standpoint, asteroids are what matter. They are the objects that cross Earth's orbit. They are the objects with impact potential. They are the objects we need to track. The distinction between comets and asteroids is not just aesthetic. It is also about predictability. Asteroids, generally speaking, are inert. They do not outgas. They do not change mass as they move through space. Their orbits are determined mostly by gravity, which makes them relatively straightforward to model over long stretches. Comets, on the other hand, are active. As they approach the sun, they heat up and release gas and dust, creating the iconic tails that make them so visually striking. But that outgassing also produces forces that change a comet's orbit in unpredictable ways. Every time a comet passes near the sun, it loses mass, changes shape, and potentially alters its trajectory. This makes long-term predictions much harder for planetary defense purposes. And that is a problem. If we cannot predict where a comet will be decades from now, we cannot assess whether it poses a threat with the same confidence. Fortunately, most comets do not cross Earth's orbit. They travel in elongated paths that take them far from the inner solar system. But some do cross. And those are the ones we watch closely. There is another class of objects that barely gets mentioned in public discussions, but keeps scientists awake at night: the unknowns. Despite decades of surveys and observations, we have not catalogued every near-Earth object. We have found most of the large ones, the asteroids bigger than a kilometer across, the obvious giants. But smaller objects in the 100 to 500 meter range are harder to detect. They reflect less light. They are often in orbits that make them difficult to observe. And yet, an object in that size range could still cause regional devastation if it hit Earth. Imagine a city-sized asteroid striking a populated area. The death toll would be in the millions. The economic damage would be incalculable. The psychological impact would reshape how humanity thinks about its place in the universe. And we might have little to no warning if the object approached from a blind spot, if it came from the direction of the sun, where telescopes cannot easily look, or if it simply slipped through the gaps in our survey coverage. This is not meant to inspire panic. It is meant to inspire preparation. The good news is that planetary defense is a real and growing field. Telescopes are getting better. Surveys are getting more comprehensive. Machine learning algorithms are helping astronomers sift through massive data sets to find objects that might otherwise go unnoticed. And missions like DART, NASA's Double Asteroid Redirection Test, have demonstrated that we can, in principle, change an asteroid's orbit if we need to. The bad news is that we are still playing catch-up. We are still finding new objects. We are still refining our models. We are still learning what we do not know. And in the realm of cosmic threats, what we do not know can absolutely hurt us. So yes, Apophis is the headline. It is the object that will pass close in 2029. The object that will be visible to billions of people. The object that will force humanity to confront the reality of near-Earth threats in a visceral, undeniable way. But it is not the whole story. It is one chapter in a much larger narrative about our species learning to navigate a universe that is beautiful, fascinating, and occasionally very dangerous. Part 6. The invisible forces that shape orbits. Let us talk about the forces you cannot see, the subtle pushes and pulls that govern the motion of asteroids over time scales longer than human civilizations. When most people think about orbits, they imagine a simple system, a rock going around the sun, pulled by gravity, following a predictable ellipse, and, for short time scales, that picture is basically correct. But zoom out to decades, centuries, millennia. The picture becomes vastly more complicated because gravity is not the only force at play. There are thermal effects. There are impacts from tiny debris. There are radiation pressures. There are electromagnetic interactions. Each one is small. Each one, taken individually, might shift an asteroid's orbit by mere meters per year, but over long enough timescales, these small forces compound into significant changes. And this is where our predictions start to wobble. The Yarkovsky effect, which we have mentioned repeatedly, is the poster child for these subtle forces. It works like this. As an asteroid rotates, one side faces the sun and heats up. Hours later, as that side rotates into shadow, it cools down and radiates infrared energy back into space. That radiation carries momentum, and because the hot side radiates more energy than the cool side, the net effect is a tiny thrust in one direction. For a spinning asteroid, the direction of the thrust depends on whether the asteroid rotates in the same direction as its orbit or the opposite direction. If it rotates prograde, the thrust tends to push it outward from the sun. If it rotates retrograde, the thrust tends to push it inward. The magnitude of the thrust depends on asteroid size, rotation rate, surface temperature, and thermal inertia. And because we do not have perfect measurements of all these properties, we have to estimate meaning. Our predictions carry uncertainty. For Apophis, scientists have measured the Yarkovsky drift at roughly minus 170 meters per year along the asteroid's orbit. That might sound small, but over the course of a 20-year observation arc, it becomes a shift of several kilometers. Over a century, it becomes tens of kilometers. Now, tens of kilometers may still sound negligible compared to the vast distances in space. But remember, gravitational keyholes are only a few hundred meters across. If the Yarkovsky effect pushes Apophis even slightly off the predicted path, it could mean the difference between missing a keyhole entirely and threading right through it. This is why scientists are so focused on refining the Yarkovsky measurements. In orbital mechanics, precision matters, and uncertainty is the enemy. But the Yarkovsky effect is only one piece of a much larger puzzle. There is also something called the Yorp effect, short for Yarkovsky, O'Keefe, Radzievsky, Padak, named after the scientists who first described it. Yorp is related to Yarkovsky, but it operates primarily on rotation rather than orbit. When an irregularly shaped asteroid absorbs sunlight and radiates it away as heat, the uneven glow can create a torque that speeds up or slows down the spin. Over millions of years, Yorp can push an asteroid faster and faster until it sheds material or flies apart, or slow the spin until it becomes tidally locked. For Apophis, Yorp is less urgent than Yarkovsky because the timescales are longer, but it is still a factor scientists must account for when modeling long-term evolution of both orbit and rotation. And then there are the truly chaotic elements, gravitational interactions with other asteroids, collisions with micrometeorites, and even solar wind pressure. Let us start with gravitational interactions. The asteroid belt is not a tightly packed ring of rocks. It is a sparse cloud where individual asteroids are separated by millions of kilometers. But occasionally, two pass close enough that their mutual gravity produces a measurable tug. For most asteroids, these interactions are negligible, but for objects in the inner solar system, where encounters with planets are more frequent. The cumulative effect of many small nudges can add up over time. Apophis, because of its close approach to Earth in 2029, will experience a significant gravitational interaction with our planet. Earth's gravity will change Apophis's orbit, shifting it onto a slightly different path than it was on before the encounter. Scientists have calculated this shift and determined that it will not send Apophis on a collision course. But it is a reminder that orbits are not static. They evolve. Now let us talk about impacts. Space is not empty. It is filled with debris, dust, grains, and pebbles left over from the formation of the solar system, or ejected from comets as they pass near the Sun. These particles are too small to track individually, but they are numerous enough that collisions happen all the time. When a micrometeorite strikes an asteroid, it transfers momentum. The effect is minuscule. A single grain of dust hitting a 340-meter asteroid is like a mosquito hitting a freight train. But over millions of years, countless impacts accumulate. And if one of those impacts happens at just the right moment, at just the right angle, it could nudge the asteroid onto a slightly different trajectory. The odds of this happening in a way that significantly affects Apophis's orbit in the next century are low, but they are not zero. This brings us to a fundamental truth about orbital mechanics. Prediction is an exercise in managing uncertainty. We can model the major forces. We can account for the big players, the Sun, the planets, the moons. We can measure Yarkovsky, calculate gravitational perturbations, and estimate the impact of solar radiation pressure. But we cannot account for everything. There are forces we do not fully understand. There are interactions we have not measured. There are variables we have not even identified. And in a chaotic system, unaccounted variables can lead to unexpected outcomes. This does not mean our models are useless, far from it. Our models are incredibly accurate over the timescales we care about most, but they are not infallible. And the farther into the future we try to predict, the more the uncertainties grow. So when NASA says Apophis poses no threat for at least 100 years, they are not lying. They are speaking based on the best data and models available. But embedded in that statement is an acknowledgement that the 100-year horizon is roughly the limit of our predictive confidence. Beyond that, uncertainties become too large to make definitive claims. This is why planetary defense is an ongoing process, not a one-time calculation. We have to keep watching, keep measuring, keep refining, because the universe is not static and neither are our predictions. Part 7. Artificial Intelligence and the Future of Threat Detection. Here is a question that rarely gets asked outside specialized conferences. What happens when the number of objects we need to track exceeds the capacity of human astronomers to track them? We are already approaching that threshold. There are currently over 32,000 known near-Earth objects, and the number grows every month as surveys improve and new telescopes come online. Each of these objects has an orbit that needs to be calculated, refined, and monitored for potential threats. Each one produces a stream of observational data positions, brightnesses, spectra, radar echoes, and each piece of data needs to be analyzed, cross-referenced, and integrated into a constantly updating model of the object's trajectory. Doing this for 32,000 objects is manageable. Barely. Doing it for 100,000 or a million is not, at least not with traditional methods. Enter artificial intelligence. Over the past decade, machine learning algorithms have revolutionized how we process large datasets in astronomy. AI can sift through thousands of telescope images in seconds, identifying objects that move against the background stars, flagging potential near-Earth asteroids, and even calculating preliminary orbits. These systems do not get tired. They do not get bored. They do not miss subtle patterns because they were distracted or overworked. They are relentless, tireless pattern recognition engines that excel at exactly the kind of repetitive, data-intensive tasks that bog down human astronomers. Modern AI systems can now detect asteroids in telescope images with accuracy rates that rival or exceed human observers. They can predict orbital uncertainties more quickly than traditional numerical methods. They can even identify anomalies objects whose behavior does not fit expected patterns, which might indicate something unusual is happening. But AI is not just about speed and scale. It is also about prediction. Remember, orbital mechanics is a chaotic system. Small changes in initial conditions can lead to large differences in outcomes. Traditional models handle this by running thousands or millions of simulations, tweaking initial parameters slightly each time, and then analyzing the distribution of results to estimate probabilities. This works, but it is computationally expensive and time-consuming. Machine learning offers a different approach. Instead of simulating every possible outcome, an AI can be trained on existing orbital data to recognize patterns and relationships that humans might miss. It can learn, for example, how different combinations of orbital parameters and physical properties lead to specific long-term outcomes. And once trained, it can make predictions much faster than traditional simulations. This is not science fiction. Researchers are already using machine learning to predict asteroid trajectories, and the results are promising. But here is where things get philosophically interesting. If we start relying on AI to predict cosmic threats, are we actually understanding the physics? Or are we outsourcing the problem to a black box? This is a real concern among some scientists. Machine learning models, especially deep neural networks, are notoriously opaque. They can produce accurate predictions without providing any insight into why those predictions are correct. You feed in data, you get out a result, and the internal logic that connects the two is buried in layers of mathematical transformations that no human can fully interpret. For some applications, this opacity is acceptable. For planetary defense, it is more problematic, because if an AI predicts an asteroid has a 10% chance of hitting Earth in 50 years, we need to understand where that prediction comes from. We need to be able to interrogate the model, test its assumptions, and verify its reasoning. Otherwise, we are making decisions about humanity's survival based on a system we do not fully understand. There is also the risk of overfitting, where a model learns patterns in the training data that do not generalize to new situations. Imagine an AI trained on a dataset of well-observed asteroids with predictable orbits. It might learn to make accurate predictions for similar objects. But what happens when it encounters an asteroid with unusual properties? An object that behaves in ways not represented in the training data? The model might confidently produce a prediction that is completely wrong. This is not a hypothetical concern. It has happened in other domains where AI is used for prediction. In planetary defense, a single wrong prediction can be catastrophic. If an AI underestimates the danger of an incoming asteroid, we might fail to act when action is truly needed. If it overestimates the danger, we might waste resources and spark unnecessary panic. Even with these concerns, the integration of AI into planetary defense is not only likely, it is hard to avoid. The volume of data we are collecting is growing too quickly for traditional methods to keep up. Telescopes like the Vera-C Rubin Observatory, expected to begin operations soon, will generate terabytes of data every night, re-imaging the entire visible sky every few days. Human astronomers simply cannot analyze all of that data manually. AI will have to do the heavy lifting. The question is not whether we will use AI, but how we will use it responsibly. How do we build systems that are transparent, interpretably, and robust? How do we validate AI predictions against independent observations? How do we ensure that the algorithms we deploy are trained on diverse, representative datasets that capture the full range of possible asteroid behaviors? These are the questions planetary defense researchers are grappling with right now. And then there is the longer-term vision, the idea of autonomous AI systems that do not just analyze data, but actively manage planetary defense. Imagine a network of telescopes, radar systems, and spacecraft guided by an AI that continuously monitors the sky, detects new threats, calculates trajectories, and even coordinates deflection missions if necessary. Such a system could react faster than human decision-making processes, potentially identifying and neutralizing threats before they become critical. But it also raises profound ethical and practical questions. Who controls the AI? What happens if it makes a mistake? What safeguards do we put in place to prevent misuse? These are not questions we can afford to ignore, because the technology to build such systems is already within reach. And as Apophis reminds us, the threats are real, part wit, planetary defense infrastructure, and its limits. Let us talk about what happens if we actually need to do something about an incoming asteroid, not Apophis, because the threat there has been ruled out for the foreseeable future. But imagine we discover a new object tomorrow, a previously unknown asteroid on a trajectory that will bring it uncomfortably close to Earth in, to say, 20 years. What do we do? The answer depends on a sprawling global infrastructure of telescopes, observatories, space agencies, and international organizations that collectively make up what we call planetary defense. And while this infrastructure is impressive, it is also incomplete, underfunded, and not as coordinated as you might hope. The first line of defense is detection. We cannot protect ourselves from threats we do not know about. This is why asteroid surveys exist. Telescopes around the world scan the sky night after night, looking for objects that move against the fixed background of stars, like faint embers drifting through a vast dark. When a new object is found, astronomers calculate its orbit and determine whether it poses any threat. Most objects do not. They are either too far away, or their orbits do not bring them close to Earth, or they are so small that even a collision would not cause significant damage. But occasionally, a survey finds something worrying, an object on a trajectory that crosses Earth's orbit, an object large enough to cause regional or global devastation, an object that might, if the calculations are right, actually hit us. That is when the second line of defense kicks in: international coordination. The International Asteroid Warning Network is a coalition of space agencies and observatories that share data and coordinate responses to potential threats. If a dangerous asteroid is discovered, the network facilitates the flow of information between organizations, ensuring that everyone has access to the latest observations and calculations. There is also the Space Mission Planning Advisory Group, which is responsible for planning and coordinating potential deflection missions. These groups do not have the authority to launch missions on their own. They are advisory bodies, but they provide a framework for cooperation, which is critical in a situation where a single country or agency might not have the resources to respond alone. Now let us talk about deflection. If we identify an asteroid on a collision course with Earth, and we have enough warning time, we can potentially change its orbit. The most straightforward method is a kinetic impactor. You build a spacecraft, accelerate it to high speed, and crash it into the asteroid. The impact transfers momentum, giving the asteroid a tiny shove. If you do this years or decades before the predicted collision, that tiny shove can be enough to make the asteroid miss Earth entirely. NASA demonstrated this technology in 2022 with the DART mission, which successfully altered the orbit of the asteroid Dimorphos by crashing a spacecraft into it. The mission was a proof of concept, showing that kinetic impact is a viable method for asteroid deflection, but it also revealed how much we still do not know. The amount of momentum transferred depends on the asteroid's composition, structure, and how it responds to the impact. Dimorphos, as it turned out, behaved more like a rubble pile than a solid rock, which changed the efficiency of the deflection. For larger asteroids, or for scenarios where we have less warning time, kinetic impactors might not be enough. In those cases, scientists have proposed other methods: gravity tractors, nuclear deflection, or even laser ablation. A gravity tractor works by parking a spacecraft near the asteroid and using the spacecraft's own gravity to slowly pull the asteroid onto a different path. This method is slow but precise, making it ideal for fine-tuning an asteroid's trajectory. Nuclear deflection, on the other hand, is the option of last resort. You detonate a nuclear device near the asteroid, not to blow it up, but to vaporize a layer of surface material. The vaporized material shoots off into space, creating a thrust that pushes the asteroid in the opposite direction. It sounds like science fiction, but the physics is sound. The problem is that nuclear deflection is risky, politically fraught, and requires technology that we have not fully developed yet. But here is the uncomfortable truth. All of these methods assume we have years, or decades, of warning. If we discover an asteroid only months before impact, there is very little we can do. We do not have the technology to build and launch a deflection mission on such short notice. And even if we did, the asteroid would be moving too fast and too close to deflect effectively. In that scenario, our only option is evacuation and damage mitigation. We move people out of the impact zone, we stockpile resources, we prepare for the aftermath. It is not a solution. It is a band-aid, and it underscores why detection is so critical. The earlier we find a threatening asteroid, the more options we have. There are also gaps in our detection capabilities that rarely get discussed publicly. Most asteroid surveys focus on the night sky, which means they cannot see objects that approach from the direction of the sun. This is not a minor oversight. It is a significant blind spot. An asteroid coming from the sunward direction would be invisible to ground-based telescopes until it was very close, potentially too close to deflect. This is exactly what happened with the Chelyabinsk meteor in 2013, a 20-meter object that exploded over Russia without warning because it approached from the direction of the sun. The explosion released energy equivalent to about 500 kilotons of TNT, injured over 1,000 people, and caused widespread property damage, and we never saw it coming. Chelyabinsk was small, too small to cause global devastation. But it was a wake-up call. It demonstrated that our detection network has holes, and those holes could be exploited by larger, more dangerous objects. The solution, according to many planetary defense advocates, is to put telescopes in space. A space-based infrared telescope positioned at a point between Earth and the Sun could detect asteroids approaching from the sunward direction, closing the gap in our detection coverage. NASA has proposed such a mission called NEO-Surveyor, designed to find and track near-Earth objects using infrared sensors. The mission is still in development, with a tentative launch date in the late 2022. If it succeeds, it will significantly improve our ability to detect threats, but until it launches, the blind spot remains. And so does the risk. Part 9. Conspiracy, paranoia, and why some people do not trust the numbers. Now we need to address the elephant in the room, the conspiracy theories, because for every official NASA press release assuring the public that Apophis poses no threat, there is a corner of the internet convinced that the truth is being hidden, that the asteroid is actually going to hit, that governments know and are covering it up, that the wealthy and powerful have already built bunkers and escape plans while the rest of us are left in the dark. These narratives are pervasive, especially on platforms like YouTube, Reddit, and certain fringe websites, and while it is easy to dismiss them as paranoia or scientific illiteracy, there is actually something more interesting happening here. These conspiracies reveal a deeper crisis of trust between the public and scientific institutions, and understanding why people believe them is important, even if the beliefs themselves are unfounded. Let us start with the basic structure of most Apophis conspiracy theories. They go something like this. NASA and other space agencies have known for years that Apophis will hit Earth. They have run the calculations, they have seen the probabilities, and they know it is coming. But they cannot tell the public because doing so would cause mass panic, economic collapse, and societal breakdown. So instead, they issue carefully worded statements that technically do not lie but obscure the truth. They say things like, no threat for 100 years, or extremely low probability. Phrasing that leaves wiggle room for later revisions. Meanwhile, the global elite are quietly preparing, building underground shelters, stockpiling resources, securing their survival while the rest of us remain oblivious. When the impact finally happens, it will come as a shock to the masses, but not to those in the know. This narrative is compelling because it taps into existing anxieties about power, secrecy, and inequality. People already feel like they are not being told the truth about a lot of things: climate change, economic instability, political corruption. The list goes on. So when they hear about a potentially dangerous asteroid, and then they hear reassurances from the same institutions they already distrust, those reassurances do not land. Instead, they sound like more of the same elites, telling comforting lies while quietly securing their own interests. Add to this the fact that asteroid science is complex, probabilistic, and filled with uncertainties, and you have a perfect breeding ground for conspiracy thinking. Because if even the experts admit there are unknowns, if they acknowledge that their models are not perfect, then maybe, just maybe, they are wrong. Or worse, maybe they are lying. The reality, of course, is far more mundane. Scientists are not hiding anything. They are doing their best to calculate the orbit of a chaotic object using imperfect data and incomplete models. When they say Apophis poses no threat for 100 years, they mean it. The calculations have been done, the uncertainties have been quantified, the risk has been assessed. But this does not mean there is zero uncertainty. Science is not about absolute certainty. It is about probabilities, confidence intervals, and best estimates. For Apophis, the best estimate is that it will not hit Earth in any foreseeable encounter. But best estimates can change as new data comes in. And that possibility, however remote, is what conspiracy theorists latch onto. There is also a psychological component to these conspiracies. Humans are pattern-seeking creatures. We want the world to make sense. We want to believe that major events have major causes and that someone somewhere is in control. The idea that a massive asteroid could just randomly happen to hit Earth with no warning and no one to blame is terrifying in a specific way. It suggests that the universe is indifferent, that catastrophic events are not orchestrated but accidental. Conspiracy theories offer an alternative. The event is not random. It is planned. There is a group pulling the strings, making decisions, controlling the outcome. And while that narrative is disturbing in its own right, it is also oddly comforting because it implies that the universe is not entirely chaotic. There is an order, even if that order is sinister. So how do we counter these narratives? Not by dismissing them outright. Condescension and ridicule only deepen the distrust. Instead, the answer is transparency. Scientists need to communicate not just their conclusions, but their uncertainties. They need to explain how the calculations are done, what the error bars mean, and why those error bars are shrinking as new data comes in. They need to acknowledge that models are imperfect and that science is a process, not a finished product. And they need to do all of this in language that is accessible to people without advanced degrees in astrophysics. Because the more opaque the science seems, the more room there is for alternative explanations to take root. But there is also a responsibility on the part of the public to engage with the information honestly, to recognize that uncertainty is not the same as deception, to understand that just because something is possible does not mean it is likely, and to resist the seductive simplicity of conspiracy narratives in favor of the messier, more complex truth. Apophis is not being hidden from you. The data is public. The calculations are peer-reviewed. The scientists are doing their jobs, and if new information emerges that changes the risk assessment, you will hear about it. Not because some whistleblower leaked it, but because that is how science works. Part D's. Imagining the unimaginable. Let us take a moment to entertain some scenarios that are by all current evidence extremely unlikely, but not physically impossible. These are not predictions, they are thought experiments. What-ifs that stretch the boundaries of what we know and explore what could happen if the universe decided to surprise us. Because while the official line on Apophis is reassuring, the truth is that we live in a cosmos that occasionally does things we did not expect, and preparing for the unexpected, even in hypothetical terms, is not paranoia. It is prudence. Scenario 1. Apophis receives an unexpected impulse. Imagine that at some point between now and 2029, a small asteroid or comet fragment collides with Apophis. The object is tiny, maybe 10 meters across, barely large enough to leave a crater, but it hits at just the right angle and velocity to change Apophis's trajectory by a few meters per second. That does not sound like much, but over the years remaining until the close approach, that tiny change compounds. By April 2029, Apophis's path has shifted just enough that instead of passing safely by Earth, It threads through one of the gravitational keyholes. The encounter with Earth in 2029 does not result in an impact, but it sets up a future collision in 2036 or 2068. We do not see this coming until it is too late to deflect. Scenario 2. Earth's gravity reshapes Apophis more dramatically than expected. Current models predict that the 2029 flyby will cause tidal effects on the asteroid's surface and rotation. But what if those effects are stronger than anticipated? What if Apophis is not a solid rock, but a loosely bound rubble pile, and the gravitational stress during the close approach causes it to partially disintegrate? Chunks of material break off, forming a debris cloud. Some of those chunks remain gravitationally bound to the main body, but others drift away on slightly different orbits. Now, instead of tracking one asteroid, we are tracking dozens, and some of those fragments might be on trajectories that bring them dangerously close to Earth in future encounters. Scenario 3. The Yarkovsky effect is stronger than we calculated. We think we have measured it accurately, but our measurement depends on assumptions about the asteroid's surface properties. What if those assumptions are wrong? What if Apophis has an unusually dark, heat-absorbing surface that amplifies the thermal radiation pressure? Or what if its rotation rate changes due to the Yorpi effect, altering the direction and magnitude of the Yarkovsky thrust over decades? This stronger-than-expected force pushes Apophis onto a different path, one that our current models did not anticipate. By the time we realize what is happening, the window for deflection has closed. Scenario 4. A binary companion is discovered. Most of our observations of Apophis have focused on the main body. But what if it is not alone? What if there is a smaller object, maybe 50 or 100 meters across, orbiting Apophis like a moon? Such a companion could have been missed in earlier observations if it is dark and close to the main asteroid. Binary asteroids are not uncommon in the solar system, and if Apophis has a companion, the dynamics become vastly more complicated. The two objects pull on each other gravitationally, affecting both of their orbits. And during the 2029 flyby, Earth's gravity could disrupt that binary system, sending the smaller object on an unpredictable trajectory, maybe toward us. Scenario 5. Planetary defense technology fails when we need it. Let us imagine that we do detect a threatening asteroid, not Apophis, but some other object on a collision course with Earth. We have 10 years of warning, which should be enough time to launch a deflection mission. We build the spacecraft. We launch it. It travels to the asteroid. But when it arrives, something goes wrong. The spacecraft's navigation system malfunctions, and instead of hitting the asteroid at the optimal angle, it glances off the surface, transferring minimal momentum. Or worse, the impact causes the asteroid to fragment, creating multiple smaller threats instead of one large one. Or maybe the deflection works, but not as well as predicted, and the asteroid is only partially redirected. Instead of missing Earth entirely, it grazes the atmosphere, breaking apart and showering the surface with debris. These scenarios are not likely. They require specific combinations of events, each individually improbable, to occur in sequence. But the point is not to scare you. The point is to illustrate that orbital mechanics is a chaotic system, and chaotic systems are by definition sensitive to small perturbations. We can model the big forces. We can account for the major interactions. But there are always unknowns, always variables we have not measured, always possibilities we have not considered. And while our models are good, they are not perfect. The universe has a way of reminding us of that fact, usually at the most inconvenient times. So what do we do with this knowledge? We prepare. We keep watching. We refine our models. We improve our detection capabilities. We develop and test deflection technologies. And we accept that some level of uncertainty is unavoidable. The cosmos does not owe us certainty. It does not owe us safety. But it does offer us the opportunity to learn, to adapt, and to protect ourselves as best we can. And that, in the end, is all we can ask for. Part owns superkilonova and the scale of cosmic violence. Now let us shift gears entirely and talk about something that makes asteroid impacts look quaint. By comparison, the death of stars. Because while we have been focused on Apophis and the relatively localized threat it might pose, the universe is busy producing events so violent, so energetic, that they dwarf anything happening in our immediate cosmic neighborhood. In December of 2025, astronomers detected an explosion designated AT-2025, and the leading hypothesis is that this was a superkilonova, a type of event so rare that it has never been conclusively observed before. To understand why this matters, we need to talk about how stars die, what happens when they do, and why some deaths are more spectacular than others. Most stars, including our Sun, will die quietly. They will burn through their hydrogen fuel, swell into red giants, shed their outer layers, and collapse into white dwarfs. No explosions, no cataclysmic violence, just a slow fade into obscurity. But massive stars, those with more than about 8 times the mass of the Sun, go out differently. When they exhaust their nuclear fuel, their cores collapse catastrophically, and the rebound produces a supernova, an explosion that can outshine an entire galaxy for weeks. Supernovas are some of the most energetic events in the universe, releasing more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. They forge heavy elements like gold, platinum, and uranium in the intense heat and pressure of the explosion. They seed the cosmos with the raw materials for planets and life. They are, in every sense, cosmic furnaces of creation born from destruction. But AT-2025 might be something even more extreme. A superkilonova is a hybrid event, part supernova and part kilonova. A kilonova occurs when 2 neutron stars collide, merging in a cataclysmic release of energy and matter. Neutron stars are the collapsed cores of dead massive stars, so dense that a sugar cube-sized chunk of neutron star material would weigh as much as Mount Everest. When 2 of these objects spiral into each other, the collision produces gravitational waves, ripples in space-time itself, along with a brilliant flash of light across the electromagnetic spectrum. Kilonovas are thought to be the primary source of the heaviest elements in the universe, the ones that cannot be produced in supernova explosions alone. But a superkilonova combines both processes. It starts with a massive star collapsing and exploding as a supernova, and then somehow involves the collision or interaction of neutron stars or black holes in the same system. The result is an explosion of almost unimaginable scale. The detection of AT-2025 was made possible by advances in multi-messenger astronomy, the practice of observing cosmic events using multiple types of signals. In this case, astronomers detected both electromagnetic radiation, light across the spectrum from radio waves to gamma rays, and gravitational waves, the faint tremors in space-time produced by the collision of massive objects. This dual detection allows scientists to piece together what happened in ways that single-wavelength observations never could. It is like the difference between hearing a story from one witness versus interviewing everyone who was there. Each perspective adds detail, context, and clarity. And what the multi-messenger data is telling us about AT-2025 is that something extraordinary happened quietly, relentlessly, out in the dark. An event so energetic it can be witnessed across billions of light years, an eruption that, in a handful of seconds, spends more power than our Sun will ever spend across its entire lifetime. Why does that matter for Apophis and for planetary defense? Because it snaps everything into perspective. We worry about a 340-meter asteroid passing close to Earth. We obsess over the tiny forces that might nudge it onto a collision course. We build telescopes and spacecraft and international coalitions to protect ourselves from cosmic debris, and all of that is necessary and quietly heroic. But the universe operates on scales so vast, with forces so overwhelming, that our local fears can feel almost impossibly small by comparison. A superkilonova releases enough energy to scorch the idea of safety itself. A shockwave from an event like that could sterilize worlds dozens of light years away. And yet we live in a galaxy where these extremes unfold calmly on cosmic clocks. The fact that we are here, That Earth has endured for 4 billion years is a testament to the sheer improbability of catastrophe arriving at our door. We live in a safe neighborhood, for now, but the universe is not, in any absolute sense, a safe place. And that brings us to an uncomfortable philosophical question. Should we fear rare high-impact events like asteroid collisions, or the far more energetic, equally rare events like nearby supernovas or gamma-ray bursts? The answer, frustratingly, is both. Because while the chance of a superkilonova occurring close enough to harm Earth is vanishingly small, the consequences would be total. There would be no defense, no deflection mission, no evacuation plan. If a gamma-ray burst from a collapsing star were aimed our way, the radiation could strip our ozone layer, bathe the surface in lethal ultraviolet, and trigger a mass extinction. And we would have no warning. Light and gamma rays travel at the same speed, so the first sign of the burst would also be the moment it arrives. Game over. But here is the thing. We cannot protect ourselves from events like that. We lack the technology, the resources, and the time. So we focus on the threats we can do something about. Asteroids, comets, near-Earth objects. These are manageable risks. They move on timescales that give us warning. They follow physics we can model. They can be deflected if we act early enough. A superkilonova, by contrast, is cosmic fate wearing a crown of fire. If it happens, it happens. All we can do is hope it does not happen in our neighborhood, in our era, and so far, that hope has been justified. Part 2's Mapping the Cosmos with Spherex. While we contemplate violent stellar deaths and the chaotic paths of asteroids, remember that humanity is also engaged in a quieter, equally profound project, mapping the universe itself. In late 2024 and early 2025, NASA's Spherex mission, the spectrophotometer for the history of the universe, Epoch of Reionization, and ICE's Explorer delivered its first full-sky infrared map. This is not just a pretty picture, though it is certainly that. It is a dataset of unprecedented scope and detail, capturing the infrared signatures of hundreds of millions of galaxies, stars, and cosmic structures. The goal is nothing less than to trace the universe's history from the first moments after the Big Bang to the present day. And while this might seem far removed from planetary defense, it is deeply relevant, because understanding the universe helps us understand ourselves, our place inside it, and the forces that shape our existence. Spherex works by observing the sky in infrared wavelengths, light invisible to human eyes, but rich with information about cool objects, distant galaxies, and the faint glow of cosmic history. Infrared can slip through dust clouds that block visible light, revealing star-forming regions, galactic cores, and the lingering signatures of ancient events. By mapping the entire sky in infrared, Spherex builds a three-dimensional picture of how matter is distributed, how galaxies cluster and interact, and how the universe has evolved over billions of years. It is a cosmic census, a catalogue of what we can see, prepared for discoveries we have not imagined yet. One of the mission's primary goals is to study the epoch of reionization, a time when the first stars and galaxies ignited, and their light ionized the surrounding hydrogen gas. A pivotal turning point in cosmic history, the transition from a dark, neutral universe to one filled with glowing structure. By analyzing the distribution and properties of distant galaxies, Spherex helps reconstruct that era, answering questions about how the first structures formed and how they shaped everything that followed. It is like forensic archaeology, but on a universal scale. We examine evidence left behind more than 13 billion years ago, piecing together a story written in faint light and deep time. But Spherex is not only looking backward, it also studies the composition of ices and organic molecules in star-forming regions within our galaxy, molecules frozen onto dust grains in the cold depths of space, the building blocks of planets, and potentially of life itself. By mapping where these molecules are found and in what concentrations, Spherex helps reveal chemical pathways, the slow climb from simple compounds to complex organics. This research matters for astrobiology, because if we understand how organics form and spread through space, we can better predict where life might arise. And that, in turn, reshapes how we think about our own existence. Are we a cosmic accident, a rare convergence of conditions, or are we part of a broader pattern, one instance of a process repeating across the stars? There is also a connection, however abstract, to planetary defense, because mapping the cosmos requires understanding the distribution of matter, the gravitational forces that shape it, and the interactions between objects and structures. The same mathematics SphereX uses to model galaxy clustering can be scaled down to model asteroid populations in our own solar system. The same techniques that identify distant star-forming regions can help reveal near-Earth objects, especially those hiding in the glare of the sun. Science is interconnected. Tools built for one purpose often become instruments for another. And the more we understand the universe as a whole, the better equipped we are to navigate our local corner of it. What SphereX ultimately gives us is perspective. When you look at a full-sky infrared map, you see billions of galaxies, each holding billions of stars, each potentially hosting countless worlds. You feel the vastness, the distance, the scale of existence. And against that backdrop, our worries about a single asteroid can seem almost trivial, but they are not trivial. They matter because we matter. Because this planet, this tiny blue marble orbiting an average star in an unremarkable galaxy, is the only home we have. Protecting it, understanding it, appreciating it is not a distraction from cosmic grandeur. It is part of the grandeur. We are the universe trying to understand itself. And that understanding begins at home, with the rocks and ice that share our solar system, before it expands outward to the farthest reaches of space and time. Part trees, dark energy, and the fate of everything. Let us venture into even stranger territory, the possibility that the universe itself does not behave the way we once believed. For decades, cosmologists worked with a relatively simple picture of expansion. The universe began with the Big Bang, and since then it has been expanding. For a while, scientists thought gravity would eventually slow that expansion, perhaps even reverse it, ending in a big crunch. But in the late 1990 seconds, distant supernova observations revealed something shocking. The expansion is not slowing. It is accelerating. Something is pushing the universe apart, overcoming gravity's pull. That something is what we call dark energy, and it makes up roughly 68% of the universe's total energy content. We do not know what it is. We do not know where it comes from. And until recently, we assumed it was constant. Enter the Dark Energy Spectroscopic Instrument, DESI, a project designed to map galaxies across billions of light years and use that map to study how dark energy has shaped expansion over time. In 2024 and 2025, DESI released preliminary results suggesting dark energy might not be constant. Instead, it could vary, growing stronger or weaker as the universe ages. This is a big deal. If dark energy is constant, the universe expands forever, growing colder and emptier until the last stars fade, and space becomes a dark, silent void. But if dark energy changes, then all bets are off. It could weaken, letting gravity slow expansion. It could strengthen, tearing apart galaxies, stars, and eventually even atoms, in a scenario called the Big Rip. Or it could fluctuate in ways we cannot yet predict, making the cosmos fundamentally uncertain on the larger scales. The implications are existential. If dark energy varies, the fate of the universe is not settled. It becomes an open problem, one we might never solve conclusively, because the timescales are immense. Billions, maybe trillions, of years into the future, and even though these events are unimaginably distant, they shape how we think about existence itself. Do we live in a universe with a fixed destiny, or one where the rules can evolve? Is the cosmos a clock winding down, or a living system capable of surprises? And here is where the connection to Apophis and planetary defense returns, softly, in abstract form. Both are stories of uncertainty. Both involve systems where unknown variables can produce radically different outcomes. Both force us to make predictions from incomplete data and to act on those predictions without perfect certainty. The difference is scale. For Apophis, uncertainty unfolds over decades and centuries. For dark energy, it unfolds over eons. But the underlying challenge is the same. How do we make decisions in the face of uncertainty? How do we balance the need for action with the humility of not knowing everything? These are not only scientific questions, they are philosophical, ethical, and deeply human. Dark energy also reminds us the universe is stranger than we ever expected. A century ago, we did not know galaxies existed beyond the Milky Way. We did not know the universe was expanding. We did not know about black holes, neutron stars, or gravitational waves. And we certainly did not know about dark energy. Each discovery reshaped reality, forcing us to revise our models and widen what we consider possible. Who knows what we will uncover in the next century? What forces, particles, or phenomena are waiting just beyond the edge of understanding? The history of science is a history of surprises, is proof that the universe is more complex, more beautiful, and more mysterious than we thought. And that pattern shows no sign of stopping. So when we talk about Apophis, or planetary defense, or any immediate concern, we should remember we are part of a much larger story. A story of a species that emerged on a small planet, looked up at the stars, and decided to learn how it all works. We are still learning. We always will be. And that is not a failure. It is the point. Part 14. Artificial intelligence listening to the universe. While we map galaxies and ponder the fate of everything, another revolution is unfolding in how we detect and interpret signals from space. Artificial intelligence has moved beyond being a tool that merely processes data. It is becoming a new lens, one that can find patterns and anomalies human astronomers might miss entirely. One of the most exciting applications is the detection of fast radio bursts. FRBs, mysterious flashes of radio energy lasting only milliseconds, yet releasing, in that blink, as much energy as the sun emits in days. We still do not fully understand what causes them. They might come from magnetars, from colliding neutron stars, from the birth cries of black holes, or from something we have not named yet. But we are finding them in increasing numbers, thanks in large part to AI systems that sift through radio telescope data in real time, identifying the signature of a burst and flagging it for human follow-up. The challenge is that FRBs are rare and fleeting. A typical radio telescope generates terabytes of data every night, recording the background hum of the universe, along with countless sources of noise. Buried in that noise are FRBs, brief spikes of energy that appear and vanish almost instantly. Finding them manually would be like searching for one specific grain of sand on a wide beach at midnight. Possible in theory, impossible in practice. AI can do it in seconds. Machine learning models trained on known FRB signatures can recognize the pattern even when it is faint, even when it is smeared by interference, and they can do it continuously, without fatigue, without distraction, without the narrow limits of human attention. The speed matters, because FRBs are not just curiosities, they are windows into extreme physics, into conditions we cannot replicate on Earth. Each detection adds a piece to a puzzle that may reveal truths about neutron stars, magnetic fields, or phenomena we have not yet imagined. Consider what happens when an FRB is detected. The AI flags the signal within milliseconds, sometimes while the burst is still unfolding. That speed lets astronomers immediately point other telescopes toward the source region, capturing data across multiple wavelengths. This rapid coordination, made possible by AI, has already led to breakthroughs. Scientists have localized some FRBs to specific galaxies, traced certain bursts to magnetars, and discovered repeating FRBs that challenge our assumptions about what engines could produce them. Without AI, most of these signals would have dissolved into noise, unnoticed, unstudied, unnamed. The machine sees what we cannot, and by seeing, it expands the border of what we know. But FRBs are only the beginning. AI is also being used to search for techno-signatures, possible evidence of intelligent civilizations beyond Earth. The SETI Institute and others have listened for decades, scanning for signals that might hint at advanced technology. It is a daunting task. The universe is vast, and we do not know what frequencies an alien civilization might use, or whether they would use radio at all. Traditional SETI searches have relied on narrow band signals, the kind produced by deliberate transmission. But what if alien technology doesn't look anything like ours? What if their signals are smeared across wide bandwidths or shaped with modulation we wouldn't recognize as language at all? AI can help by searching without preconceptions, looking for any pattern that departs from nature, whether it matches our expectations or not. The quiet beauty of machine learning here is its agnosticism. Our human astronomer, even with the best intentions, brings assumptions. Conscious or not, we carry a picture of what a transmission should be, radio broadcasts that resemble our own, structured in familiar ways, echoing our technological history back at us. But a civilization millions of years older might communicate in ways that feel like static to us, using encoding schemes we've never imagined, sending meaning through forms that don't look like meaning until you learn the grammar of their physics. An AI trained on oceans of cosmic signals might notice structure inside what we'd call chaos. It might catch correlations between seemingly unrelated events. It might flag a signal no human would think to investigate, not because it is magical, but because it is patient and tireless and willing to look everywhere at once. This doesn't guarantee contact, but it expands the search space enormously. Instead of hunting a needle in a haystack, we teach the machine to recognize anything that doesn't belong in the haystack, no matter what the needle looks like. And there's an even stranger possibility. AI may detect something we don't yet know to look for at all. We've seen this pattern elsewhere. AI has helped discover new drugs, found disease markers in medical images, and predicted protein structures with striking accuracy. There's no reason the same approach can't work in astronomy. A model trained on vast cosmic data could reveal anomalies, correlations, new phenomena, new questions. It's speculative, yes, but it's also the frontier of how science is changing. Imagine an AI trained on decades of radio data, infrared surveys, X-ray skies, gravitational wave catalogs. It has watched millions of stars, thousands of supernovas, uncountable galaxies. It knows what normal looks like across every wavelength we can measure. And then, one night, it flags something. Not an FRB, not a neat techno-signature, something else. A pattern in how certain stars behave near black holes, a correlation between gamma-ray bursts and gravitational waves no one thought to test. A subtle periodicity in the cosmic microwave background, hinting at structure beyond what we can see. Discoveries like that wouldn't begin with a tidy hypothesis. They would rise from the data itself, patterns emerging organically. When a sufficiently powerful algorithm explores without human blinders, that is a new way of doing science, and it's already producing results. But there are risks, real ones. AI can generate false positives, seeing meaning where there's only noise. It can be vulnerable to adversarial inputs, signals crafted to fool it, and it can overfit, becoming excellent at recognizing the familiar, then failing when it meets something truly new. These concerns demand validation, testing, and restraint. They don't erase the promise, they define the responsibility. AI works best with human oversight and a steady, gentle skepticism. False positives are especially thorny in astronomy because the signals are often faint, buried beneath a restless background of cosmic noise. An AI might flag thousands of candidates, and human astronomers still have to sift through them, separating the real from the artifact. That takes time, and it can overwhelm the very scientists AI was meant to help. The answer isn't to abandon AI, it's to improve it, to train better models, to build systems that estimate confidence and prioritize the most promising leads. It becomes a conversation, back and forth, between astronomers and machine learning researchers. And it's working. False positive rates are falling. Detection accuracy is climbing. The tools are getting sharper, quieter, more reliable. The parallel to planetary defense is obvious. Just as AI helps us catch FRBs and hunt for techno-signatures, it also helps track asteroids, model orbits, and forecast risk. Same principles, huge datasets, subtle patterns, the need for speed and precision. And just as AI might one day detect a signal that changes our view of the universe, it might also detect an asteroid that demands immediate action. The tools we build for one purpose often serve another. In the end, it's all part of the same project, learning to navigate a universe that is complex, surprising, and sometimes dangerous. But there's a deeper implication here, beyond faster analysis. AI is changing our relationship with the cosmos. For most of history, we explored space with our senses, extended by instruments we controlled. Telescopes stretched our vision. Computers stretched our calculations. But we were always the ones choosing what to look for and how to interpret it. AI shifts that balance. It becomes an autonomous explorer, a partner in discovery rather than a passive tool. It notices what we didn't ask it to notice. It connects dots we didn't know were there. And in doing so, it can reveal aspects of reality that might have stayed hidden indefinitely. This isn't replacing human scientists. It's multiplying their reach, giving them new eyes for the night sky and new questions to carry into the dark. And as we stand near events like Apophyse's approach, as we contemplate stellar violence and the mystery of dark energy, we need every advantage we can build, because the universe will not slow down for us. It won't simplify itself to match our understanding. It will keep offering challenges, some predictable, some utterly unforeseen. If we want to survive, to thrive, to understand our place here, we have to embrace tools that extend us beyond human limits. AI is one of those tools, and it's only beginning. Part Keynes, the future we are building. So, here we are, near the end of this long journey, through asteroids, explosions, dark energy, and the machinery of awareness. Let's gather it all into one question. What are we actually doing about any of this? Because knowledge without action becomes trivia, and the stakes are too high for trivia. The future of planetary defense, the future of our species' ability to detect and respond to cosmic threats, is being built right now. Not in some distant hypothetical era, right now, through international cooperation, technological innovation, and a growing recognition that we are not passive observers. We are participants, and survival asks us to act like it. The International Asteroid Warning Network, IAWN, is one cornerstone of that effort. It isn't a single agency. It's a coalition, space agencies, observatories, research institutions worldwide committed to sharing data and coordinating responses to potential threats. When a new near-Earth object is discovered, IAWN helps information move quickly, so everyone has the latest observations and calculations. It sounds mundane, but it's quietly revolutionary. For most of human history, nations competed in space, racing to plant flags and claim prestige. Planetary defense demands something different. It demands cooperation. An asteroid doesn't care about borders. If one is headed for Earth, it is everyone's problem. Solving it means pooling resources, expertise, and observations. The network works through designated nodes across countries and organizations. If an observatory in Chile detects a new object, that information can flow to nodes in the United States, Europe, Japan, and beyond. Other telescopes can begin tracking immediately from different angles, latitudes, hemispheres. This distributed approach isn't only redundancy, it's coverage. Earth turns. The sun rises and sets. A telescope in Arizona can't observe an asteroid in daylight, but a telescope in Australia can. Coordinated globally, we can maintain near-continuous monitoring of potentially hazardous objects. Fewer gaps, fewer blind spots, fewer quiet hours where something could shift unseen. Alongside IAWN is the Space Mission Planning Advisory Group, SMPAG, focused on the operational side. If a real threat is identified and a deflection mission is needed, SMPAG helps coordinate the plan. Who launches, who pays, who decides strategy? These aren't small questions. They involve politics, economics, international law. SMPAG exists to navigate that complexity, so if the day comes when we must act, we're not starting from nothing. And yes, it's easy to be cynical about international bodies, but their existence matters. It means we are building infrastructure, slowly, imperfectly, but deliberately. Consider what SEMPAG is trying to solve. Imagine we discover an asteroid that will impact in 15 years, with high certainty, the impact point, the Pacific Ocean, a collision that could trigger tsunamis across multiple coastlines, millions of lives at risk. SMPAG's role would be to coordinate a global response. Which agency can launch on the needed timeline? Do multiple agencies collaborate, merging technology and expertise? How do we choose a method? Kinetic impactor, gravity tractor, nuclear option, and who makes that decision? The country with the biggest space program, a vote among nations. The scientists closest to the data. There are no easy answers, but these answers must exist before a real crisis arrives. SMPAG works through scenarios now, running exercises, drafting protocols, building shared expectations, because when the real threat arrives, there won't be time to argue over procedure. The plan must already be written, ready to execute. Then there are the missions. NASA's DART mission proved kinetic impact can work, that we can change an asteroid's orbit if we act early enough. But it also exposed how much we still don't know. Deflection efficiency depends on composition, structure, and response to impact. Dimorphos behaved more like a rubble pile than a solid monolith, and that changed the outcome, in some ways making the deflection more effective. But what if the next asteroid is solid rock? What if it's a binary system? What if it's spinning in a way that complicates targeting? These questions guide the next generation of missions, being planned right now. OSIRIS Apex, the repurposed OSIRIS-REx spacecraft, is headed for Apophis to study how the 2029 flyby affects it. ESA's Ramses concept aims for similar goals. Each mission teaches us, refines our models, improves our readiness. This data isn't academic window dressing. It has practical consequences. When OSIRIS Apex observes how Earth's gravity alters Apophis, we learn how tidal forces reshape surfaces, how spin states shift, how loose material migrates. That knowledge feeds directly into deflection planning. If we understand gravitational stress responses, we can better anticipate how an asteroid might respond to an impactor or other interventions. If we can infer internal structure, fractured or monolithic, porous or dense, we can choose methods more wisely. Every measurement, every image, every radar echo makes us incrementally better at protecting ourselves. This is not abstract curiosity. It's survival engineering done quietly, one dataset at a time. But technology alone isn't enough. We also need detection, early detection. This is where the Vera-C, Rubin Observatory and NASA's NEO surveyor come in. Rubin will scan the sky repeatedly, generating a river of discoveries, revealing countless new near-Earth objects. NEO surveyor, in space with infrared vision, can reduce the dangerous sunward blind spot, catching objects that ground-based telescopes struggle to see. Together, they improve our ability to catalog and track threats. But they're expensive. They require funding, political support, time. And in an era of competing priorities, it's hard to sell protection against a disaster that may not happen soon. Still, the economics are starker than most people realize. Planetary defense costs billions over decades. A major impact costs trillions, perhaps tens of trillions, when you count lives, infrastructure, long-term disruption. Even a 50 to 100 meter object could devastate a major city. The damage would dwarf the cost of preparedness. As insurance policies go, this is one of the best humanity could buy. But insurance is a difficult story to tell because success is invisible. You can't hold up the asteroid that didn't hit Earth and declare victory. That makes planetary defense politically vulnerable, which is why public awareness matters. The more people understand the reality of near-Earth threats, the more they'll support efforts to address them. And events like Apophis's 2029 flyby will change awareness in a visceral way. When millions look up and see a mountain-sized rock passing close enough to thread near our satellite realm, the idea stops being abstract. It becomes immediate, unforgettable. That moment could catalyze a new era of investment, not from panic, but from clarity. A sober recognition that the universe sometimes throws rocks, and we have the ability and the responsibility to respond. The 2029 flyby will be a global teaching moment. Schools will hold viewing nights. Museums will build exhibits. News outlets will tell the story in slow motion. For a brief window, the whole world will think about orbits and risk and resilience. That awareness doesn't vanish completely. It shifts the baseline of what people care about. And when budgets are negotiated, a public that understands planetary defense is more likely to support it. The challenge is sustaining attention after Apophis passes safely, after people return to daily life and the sky feels distant again. Sustaining momentum requires education, transparency, steady progress. Every asteroid catalogued, every simulation refined, every test conducted, every agreement signed. These become quiet milestones that keep readiness alive. But we should be honest about limits. We cannot defend against everything. A nearby superkilonova, a gamma-ray burst, truly extreme events are beyond our current capabilities. If they happen, they happen. But asteroids and near-Earth objects are different. They operate on timescales that often give warning. They follow physics we can track. And if we invest in detection and deflection, we can reduce risk meaningfully. Not perfectly, not with absolute certainty, but enough to matter. And in a universe built on uncertainty, enough is sometimes the most rational victory available. So, as we watch Apophis approach, as we track 3I, Atlas drifting harmlessly far away, as we contemplate stellar violence and dark energy, remember this. We are the first generation with the tools to detect cosmic threats and potentially do something about them. That is a responsibility and also a rare privilege. We are not helpless. We are not required to accept fate without preparation. We can learn, we can plan, we can act. And if we do it well, if we build infrastructure and keep it alive, then when the next Apophis comes, when the real threat appears, we may be ready. Not because we got lucky, but because we chose readiness. The universe does not stop. It does not care about our fears or our schedules, but we are here, on this small planet, looking up, with instruments powerful enough to see across billions of light years and precise enough to track a building-sized rock in the dark. We've built a civilization that can calculate trajectories decades ahead, launch spacecraft, test deflection, coordinate globally. That capability is new. It is fragile. It is incomplete. But it exists. And every year it gets steadier. Every mission expands our understanding. Every observation tightens the orbit of uncertainty. Every agreement strengthens the mesh of cooperation. We are learning to become a spacefaring species, not just explorers, but stewards of our relationship with the cosmic environment we live inside. Apophis is not the end of this story. It's a chapter, a milestone, a moment when we prove to ourselves that we're paying attention, that we can be calm and prepared at the same time, that we will watch, measure, and act when action is possible. Not because the universe is gentle, but because we are capable, because we can choose to be. The cosmos will keep presenting challenges, some predictable, some astonishing. If we want to survive, thrive, and understand, we can't ask the universe to simplify. We have to expand. We have to build tools, build trust, build plans, and keep them ready in the quiet years, not only the dramatic ones. Apophis is a rehearsal and a reminder. A visible sign that the sky is not decoration, it is dynamics. That orbit is not destiny. It is a calculation we keep improving. And that preparedness is a choice we make over and over, patiently, together. Because the universe won't protect us, so we learn to protect ourselves, and we do it without panic, with clear eyes, steady hands, and the simple belief that survival is worth fighting for.